Hey everyone, and welcome. Today, we're going to pull back the curtain and look at the modern Deep Learning Toolkit, basically how AI actually works under the hood. We're going to see the ingenious solutions that took deep learning from this cool idea on a whiteboard into the world-changing force it is today.
I mean, think about it. Deep learning is everywhere. It's the engine running behind the scenes of so many things we just take for granted now. That speech assistant on your phone? That's deep learning. The eerily good product recommendations you get online? Yep, that too. All the way to incredible advances in medical diagnostics. It really is the invisible architecture of our modern world. But here's the thing that's kind of wild. The basic idea of neural networks has been around for ages. The real dream was to make them deep, with tons and tons of layers, but for the longest time, it was just impossible. They were a brilliant idea that simply didn't work in practice. So the big question is, what changed? What finally unlocked all that potential? Okay, so let's start with the first massive roadblock. As researchers tried to stack more and more layers to build deeper networks, they just kept hitting a wall. The problem was that the learning signal, the very feedback the network needs to get smarter, would either vanish into nothing or just explode into nonsense. This is famously known as the vanishing or exploding gradient problem, and it's the perfect name for it. It's like you're playing a game of telephone with 100 people. By the time the message gets to the end, it's either completely gone or it's become some distorted, crazy version of what you started with. That's what was happening inside these networks, and it just brought learning to a dead stop. So it was pretty clear what needed to happen. Researchers had to invent a totally new kind of building block, a smarter, more reliable type of artificial neuron that could pass that learning signal from one end of a super deep network to the other without it fizzling out. And the solution that won out is honestly beautiful in its simplicity. On the left, you've got the old way. See how those curves flatten out at the top and bottom? That's where the signal gets squashed. But on the right, you have the modern approach, the rectified linear unit, or ReLU. And its rule is just so simple. If a number is negative, make it 0. Otherwise, just let it pass through. That's it. This tiny, elegant change was an absolute game changer. It let the learning signal flow deep into the network. Okay, so we've got our better building blocks. Problem solved, right? Well, not quite. Fixing that first problem just helped us see the next one more clearly. It turns out, training a neural network is like being dropped into a massive, foggy mountain range with millions of dimensions and being told, okay, find the absolute lowest point. Yeah, this lost landscape isn't some nice, smooth bowl where you can just roll to the bottom. Oh no, it's full of traps. You've got local minima, which are like little valleys that trick you into thinking you've found the bottom when the real Grand Canyon is just over the next ridge. Then you've got these weird, flat saddle points that can just stop your progress cold. So to get through this crazy terrain, a simple instruction like just walk downhill is basically useless. You're going to get stuck. What we really needed was a much smarter navigation tool, a better compass, a better map, basically a high-tech GPS for this insane landscape. And this is exactly what we got. The solution evolved over time. We started with the basics. Just take a small step in the steepest direction. Simple, but yeah, it gets stuck. Then we added momentum, the idea that a ball rolling down hills should build up speed to coast over the little bumps and flat spots. Finally, we get to modern optimizers like Atom, which are the whole shebang. They have adaptive rates, which means they can take big, confident leaps on the easy parts and then slow down and take tiny, careful steps when the terrain gets steep and dangerous. So now, we've got great parts and a fantastic GPS. Our networks are learning faster and deeper than ever before. Success! Except they got so powerful, they picked up a new, really bad habit. They became geniuses at memorizing. This is a classic machine learning problem called overfitting. And the best analogy is that student who's amazing at the practice test. Why? Because they just memorize the answer key. They can get a perfect score on those exact questions. But the moment you give them a new problem that tests if they actually understand the material, they're completely lost. That's overfitting. So just look at this squiggly line. It's a perfectionist. It's twisting and turning to hit every single one of those data points. It gets an A+ on the training set. But in the process, it's also memorized all the random noise, all the little meaningless wiggles. This model isn't smart, it's brittle. It hasn't really learned anything. Now contrast that with this line.
See how it's smoother? It's not hitting every single point. It's okay with being a little bit wrong here and there, because what it's doing is capturing the real pattern, the underlying trend. This is a model that has actually learned, one that can generalize to new data. So the big question is, how do we force our genius model to learn like this instead of just memorizing?
Well, the solution is pretty clever and a little counterintuitive. It's a form of strategic sabotage called regularization. Basically, you have to make the learning process just a little bit harder to stop the network from taking the lazy path of pure memorization. And one of the most elegant ways to do this is a technique called dropout. The idea is brilliant. Imagine you have a team of expert neurons. With dropout, for every single new problem you give them, you randomly tell a few of them, hey, you guys sit this one out. Take a break. So what does this do? It means no single neuron can get lazy. No neuron can afford to totally depend on another specific neuron to be there to help out. Every single one is forced to pull its own weight and learn features that are useful on their own, because they never know who their teammates are going to be on the next problem. It's like forcing teamwork by constantly shuffling the team.
So, as you can see, these aren't just a few random tricks. These are fundamental pillars that work together. They form the essential toolkit that nearly every single modern deep learning system is built upon today.
So let's just do a quick recap. Problem 1, our signals were vanishing. The solution? Better building blocks, like ReLU. Problem 2, we were getting lost in a complex landscape. The solution? A smarter compass, like the Atom Optimizer. And problem 3, our models were just memorizing everything. The solution? Force them to work as a team using dropout. And that really leaves us with one final thought. This incredible toolkit solved the huge, show-stopping problems that held AI back for decades. It's what enabled the revolution we're living through right now. But the journey is, of course, far from over. Every powerful solution opens up a whole new set of even more complex, more interesting challenges. So the question for us now is, what comes next?